All right, let's dive right in. Today, we're going to pull back the curtain on how your computer actually thinks. We're going to explore the simple, really elegant logic that allows a machine to go from being just a simple switch to doing complex math.
I mean, it is kind of magical when you think about it, isn't it? These incredibly powerful devices we use every single day are, at their very core, just a massive collection of switches that can only be on or off. So how do you get from a simple yes or no to calculating rocket trajectories?
Well, the answer isn't to design one impossibly complex, chaotic megacircuit. Nope. Instead, engineers use a much more elegant and powerful idea. It's kind of the secret weapon of digital design, and it's called regularity.
So what does regularity actually mean? It means instead of reinventing the wheel for every single bit we want to process, we design one simple, perfect little building block, and then we just repeat it. We stamp it out over and over and over again to build something much bigger. It's exactly like building a massive wall using thousands of identical bricks.
Okay, so before we can even think about adding numbers, we have to solve a more basic problem, just getting the data to the right place. You can think of it as the plumbing of the processor. We need circuits that can direct the flow of information.
The first key component here is the multiplexer, or MUX for short. Imagine a bunch of train tracks all trying to merge into one main track. The MUX is like the switch operator who decides which train gets to go onto that main line. It takes a whole lot of inputs and selects just one to pass through.
And, at its core, it's incredibly simple. A basic 2-to-1 MUX has two data inputs, let's call them D0 and D1, and a single control wire, S. If that control signal S is a 0, then D0 gets sent to the output. If S is a 1, D1 gets sent through. That's it. It's a fundamental decision-making circuit.
Our second routing component is the decoder. Now, if a MUX is about choosing one of many inputs, a decoder kind of does the opposite. It takes a compact binary code as input and activates one and only one of many possible output lines. It's like a postal worker reading a zip code to deliver a letter to a single specific house.
So you should really think of them as two sides of the same coin. A MUX is a selector. It funnels many data streams down into one. A decoder is an activator. It uses a single code to enable one specific device or path. You absolutely need both to manage all the data traffic inside a processor.
All right, so we can route our data. Awesome. Now let's see how we can use that to do some actual math. But first, we hit this subtle but absolutely critical roadblock. Computers love using binary for positive numbers. But what on earth do they do with negative ones?
I mean, representing the number 5 is easy, right? It's just 101 in binary. But how do you represent -5? You can't just stick a minus sign in front of the bits. We need a system that the hardware can actually understand and work with directly.
And the solution that everyone uses is this beautiful piece of mathematical elegance called 2's complement. The reason it's so brilliant is that it makes subtraction behave exactly like addition. And that one trick, as we're about to see, dramatically simplifies our entire hardware design.
The process itself is beautifully mechanical. To get -5, you start with +5 in binary. First, you just flip every single bit. Every 0 becomes a 1, and every 1 becomes a 0. Then you just add 1 to whatever you got. That's it. That specific pattern of 1s and 0s is how a computer internally represents -5. Okay, we have our numbers and we have our routing. It's finally time to build. We are going to construct the circuit that does the most fundamental operation in all of computing, addition.
We start with the smallest possible piece, the half adder. All this little circuit does is add two individual bits together, and it gives us two outputs, the sum and a carryout for when that sum is too big to fit in just one bit.
If you look at its truth table, most of it is pretty straightforward. 0 plus 1 is 1, 1 plus 0 is 1, but look at that last line, 1 plus 1. In binary, that's 2, which is written as 1, 0. So the sum bit is 0, and we generate a 1 on the carryout line. We're literally carrying the 1 just like you learned in grade school math.
But here's the catch. When we do addition by hand, we have to handle carries coming from the column to the right. Our simple half adder has a carry out, sure, but it has no place for a carry in. That means it can't be part of a chain, which makes it pretty much useless for adding numbers bigger than one bit. So we upgrade to the full adder. This is our perfect repeatable brick. It's almost the same as the half adder, but with one crucial addition, a third input, specifically for the carry in. Now it can accept a carry from the adder next to it, do its own addition, and then generate a new carry for the next one in the chain.
And this, right here, this is the magic moment. With the full adder, we have a component that we can just copy and paste. We can chain them together to add numbers of any size. This is that principle of regularity we talked about, in action.
To build an 8-bit adder, we just take 8 full adders and line them up. The carry out from bit 0 becomes the carry in for bit 1, the carry out from bit 1 becomes the carry in for bit 2, and so on. The carry ripples down the line, kind of like a series of falling dominoes, until the final sum is all calculated.
So, we've built an adder. But so what? Why does this one circuit matter so much? Because this simple ripple carry adder we've just designed is the absolute core of the computer's mathematical brain.
That brain is called the Arithmetic Logic Unit, or ALU. Every single time your computer performs addition, subtraction, or logical operations, like and or, it's the ALU doing the heavy lifting. And the adder we just designed is its centerpiece. And now for the final, brilliant twist. Remember 2's complement? This is where it all pays off. It turns out that subtracting a number is mathematically identical to adding its negative counterpart. A minus b is the exact same thing as a plus negative b. This means our single adder circuit can now do double duty. To perform subtraction, the ALU simply takes the second number, uses some simple logic gates to find its 2's complement, and then feeds it right back into the very same adder circuit we already built. One piece of hardware for 2 essential arithmetic operations. That is the essence of elegant design. And this adder, combined with other simple logic gates for operations like and or, forms the powerful core of the ALU.
And that brings us right back to our core idea, regularity. We went from a simple switch to a complex calculator, not through brute force, but by finding a simple, elegant, repeatable pattern. It makes you wonder, what other marvels of modern computing, from massive memory arrays to entire processors, are ultimately just built from the clever and beautiful repetition of simple ideas?